Okay, so go ahead to register on the website. So you can continue, and right now let us discuss the results of chapter 6. Same weather moment. Well, that's we've discussed the possible candidates of input distribution, including the possible examples from the continuous random variable. That is the continuous probability density function, and also the discrete type. And finally, we already have these. All right, so this one, it says we have the empirical one. We can construct the CDF. Well, maybe you have a question. Normally, we want to have a PDF or PMF, but why here we only have a CDF? Why CDF only? I think in chapter 8, you will know, in fact, if you want to generate a random variable, it is not necessary to use PDF. We can use CDF. So that's why we construct the CDF for empirical, actually for data, so that we have the empirical distribution. So if so, then it is a must to have a CDF rather than the PMF or PDF. So that's why for the empirical distribution, we describe the CDF simply. All right, so those are the useful probability distributions. And right now, let us check this one first. If we want to know for example, maybe two observations, and we want to make sure, are they independent? If I want to check that one, so we need to verify sample independence. So how to do? Here, look at these. You can observe, right? And of course, sometimes they are not independent, right? For example, you can look at some temperature, all right? And actually, they are not independent. But possibly, we may make sure independent or not. So this is the purpose of the technique. We want to make sure they are independent or they are dependent. In the following, we can use the graphical techniques by using correlation plot or by using the scatter diagram. And of course, you can apply some tests. All right, so you can use actually it should be the von Neumann. Okay, von Neumann. All right, so we can have some tests. And for the test, of course, we can have some requirement. For example, here, we do not expect to have the equal value in the data. All right, so this one, of course, we need to have some requirement. However, look at this. If we have the requirement, if we consider discrete data, sometimes we have the equal value, and then it's hard to meet the requirement. All right, but actually, if we want to test the independence using this way, we need to avoid that. Actually, you can have the test and so that you have the result. But we focus on the graphic technique in the following. First of all, here we have the correlation. Correlation, you simply follow the definition of chapter 4. And then you have the correlation plot. So how to calculate? You 0. We expect almost 0, and then we have this. Okay, wait a moment. Maybe some internet problem. Let me try to avoid some of the problems. Wait a moment. Okay, so it says if we have that one, we expect to have almost 0. To make sure these samples are independent. All right, so this one is really direct. You have the correlation plot. And if we want to have independence, we use 0 correlation. Well, you have a question. Independent imply 0 correlation. However, this one, is it true? Of course, no. Generally, not true. But we don't have any choice. We simply use correlation and try to think about 0 and then enforce independence. All right, so we use 0 correlation, but 0 correlation cannot ensure independence actually. However, no choice. We only use these to have the inference. They are independent. Okay, so here it doesn't mean the zero correlation can imply independence, but we use this assumption, zero correlation, and somehow like they are independent. Well, this is the first one, using zero correlation to verify sample independence. Although it is not generally true, but we apply this. So this is the first one, correlation plot. And previously we have a zero correlation, but right now, how about this? Not zero correlation. It says we want to know the queuing data. And this one, actually, you have the non-zero correlation for some interval. All right, so for example here, the interval, and also some of the interval. All right, so it is not zero actually. So this one, you can understand they are not independent. All right, so you can have the previous observation. It says you can have the plot. All right, and I let you know independent then imply correlation, a zero correlation. But actually, these one not true. However, we take it. All right. So this is the first one, correlation. And next one, if the data are dependent, then maybe they have some trend, or otherwise we should have some specific pattern to imply independent. Okay, so how to make sure they are independent? If you use a pair, how to have the pair? You have the adjacent data. So I and adjacent data I plus 1. Okay, and next one you can, for example, x sub 1 and s sub 2, and next one s sub 2 and s sub 3. You can have the plot. Such a plot, it is called the scatter plot. If we have the scatter plot, and if no specific pattern, for example, random, and then we can make sure they are independent. Or maybe we have a vertical line or horizontal line. It says the adjacent data is irrelevant to the next one. So you can use the three possible patterns: random, vertical line, or horizontal line, and then you can make sure you have the independent data. All right. Okay, so you can use this way. And the same, previously we have a zero correlation, right? And right now, how about the pattern here? Do you think you have the random scatter diagram? Maybe not really sure, but if someone that you know seems to be random, and can you accept at this moment? Maybe still can accept. However, if we have MN1 non-zero, so you should have independence. And here, look at the somehow like you have the trend here. So of course you have some possible correlation, right? And look at this again. So can you have some specific trend? Seems to be no, but maybe you feel still not totally random. All right, why not totally random? Look at this. It is not zero correlation at all. So of course we may have some possible independence, a possible dependence. So that's why even if someone that you know about the scatter diagram, it seems to be you have the random pattern, but you still feel, well, perhaps you can find some specific trend. even you cannot, it is not hard for you to tell. So that's why I use zero correlation first and ask you to check the scatter diagram and try to convince you for this figure. Perhaps we try to treat them as a random, and so that you have the random scatter diagram. And this one actually, I think you can look at these. We have some trend. So that's why we can make sure this one you don't have the independent data. So this is the graphical techniques. And previously, I let you know if I want to check some test, you can try to refer to the test book if necessary. I only let you know the graphical technique. So that's why we have the correlation plot and the scatter diagram simply. So if you want to have some detailed results, you can try to check the test book, and then you can understand some of the further details for the test, using test to make sure you can have the independence or dependence. Okay, so that's it up to now. Any question? All right, I assume no question. And right now, we are reaching the 3 activities. Activity 1, we want to select one family of distributions. Here we call hypothesizing families of distributions. For example, how about exponential? If we have an exponential, in fact, we may have a parameter. So next activity, you want to make sure the detail, then you can determine the parameter. Once you can determine family and parameter, and then we want to make sure acceptable. So you need to determine how representative the Philly distributions are. Let's say if you have the family and also you have the parameter, you need to make sure how proper the selected distribution is. So this is activity 3. So in the following, let us check the 3 activities. So activity 1 asks you to have the process of determine appropriate general family of distributions. And this one actually based on some of sample data. For this one, initially we don't care about parameter because right now we don't know, so it is not necessary. So it doesn't mean you need to have all the correct parameter to have the family of distribution. All right. And if you determine the family of distribution, sometimes you may have some prior knowledge. Prior knowledge allow you to make sure or try to rule out some impossible distribution, and so that you can try to think about which family of distribution will be suitable. Okay, so if we want to know some of the prior knowledge, some useful summary statistics perhaps you can apply. So later we will look at the table 6.5, and later you can use that statistic to have some prior knowledge. Based on the prior knowledge, you can try to select some possible family or try to rule out some impossible family. All right, so for example, think about this form of family to use. Well, exponential, gamma, or what else? Actually, I let you know after the selection of family of distribution, you need to estimate parameter, right? And finally, you need to assess goodness of fit. Well, previously, I let you know we can have prior knowledge, but sometimes you don't have the prior knowledge. Okay, and actually, you don't have enough prior knowledge. So it doesn't mean you have all. Well, should we have enough prior knowledge and then we can select the family of distributions? Sometimes no. It doesn't mean you should have the enough prior knowledge to select the distribution. I mean the family of the distribution. For example, if you have the first one, arrivals one at a time and constant mean rate and the independent actually all the time follow the exponential inter-arrival times. If you have these, what that means, it seems to be suggest Poisson. Even you don't have enough information, but at least this one can suggest the Poisson distribution or the Poisson process. And furthermore, if sum of many independent pieces, and possibly you can use normal. And product of many independent pieces and then log normal. Well, why log normal? Look at this. If we have A and B, taking logarithm. So you have A plus B. Okay, so logarithm, we have the sum of the individual logarithm. And then if they still follow the concept from the second item, of course, you can try to use that one. This one follow normal. And taking logarithm follow normal. So of course, you can have the log normal to serve as the distribution for the current discussion, right? All right, so sometimes it is not necessary to have the complete or enough information, prior knowledge. And then you can have the possible suggestion. For example, you have these, Poisson and the normal and log normal. So these are possible choice. So the limited information to have the suggestion. Okay. And next one, it says sometimes we can rule out distributions based on some possible information, for example, range. All right, for normal you have the negative part. If you don't want to have the normal, if you don't have the negative value, and then it is not possible to select normal. All right, so sometimes you can pass on some information to rule out the distribution. And sometimes if you insist to have the possible distribution based on normal, and then you need to have the reshaping. What that means reshaping, you need to based on the possible part and based on the normalization, and so that you still try to use that family of distribution. However, this one, if you use this one, it says you try to enforce yourself to select that one, even it is not appropriate. You see, even it is not appropriate. So it doesn't mean you always need to do so. But sometimes if you prefer to do so, you still can do, but you need to modify the distribution of the original standard distribution. Okay. Well, I think you don't want to do so, but I just let you know. Sometimes if you want to do, you can do it, but don't forget you need to normalize. And sometimes you can compare some simple sample statistic so that you can have some idea. For example, if you have a sample mean, and also you can have a median, and if they are close, and this information suggests a symmetric distribution. All right, and also you can have, for example, coefficient of variation of a distribution, CV, or lattice ratio of a distribution. What is the definition here? Standard deviation over mean. And how to have the estimation? Use the square root of sample variance and over the sample mean. If we have this value and meet 1, 2, and 3, and then we have the 3 possible results. And wait a moment, for the results, if we check standard deviation over its mean, and right now, is it true? When alpha alpha lower than 1 and alpha greater than 1, perhaps we choose gamma first. So right now, let's check gamma to make sure this one true. So that you have a CV lower than 1. So let's get back to check these. You can look up your taskbook, but right now I look up the slides to illustrate, is it true? All right, maybe we can use gamma first. Gamma, right? For gamma, we have this. CV equal to this one. Right? And the mean, this one. So finally, we have a beta canceled. And we have this one. All right. So if we have a CV, this one follows square root of alpha, 1 over square root of alpha to have a CV for gamma distribution. Well, if so, let us go back to the discussion. Here, CV greater than 1, so this one, CV lower than 1, right? So lower than 1 says this. All positive, so you have this. If we have this, so it says alpha should larger than 1. So that says incorrect. We should have the correction. We should have the correction. All right, so if you check gamma and then you will understand not true. So you should have CV lower than 1 when alpha greater than 1 and CV greater than 1 when alpha lower than 1. Okay, when alpha is lower than 1 and then you can have CV, the CV value greater than 1. All right, so this is the first one. You need to have actually you need to recheck, and then you will understand. For alpha, actually the range, they should be changed to the current one. Alpha greater than 1 to alpha greater than alpha lower than 1, change to alpha greater than 1, and etc. So actually you can use that one. And next one, how about exponential? here, exponential for CV. So that's why CV equal to 1 only suggests exponential. This one. Okay, so CV, and then you can have the possible selection if you want to use gamma or exponential. All right. So this is CV, and actually you can check next one. Before we check next one, CV, later you can understand gamma. So what is the distribution? Continuous. And lattice ratio, actually we check discrete distribution. And right now, I do not go back to check the results for you. But if we have a lattice ratio lower than 1, then you should choose binomial. Equal to 1 person, and greater than 1, you can choose binomial. Sorry, negative binomial. And negative binomial, of course, include geometry. All right, so if you can have the statistic, you can have the selection as well. All right, so this is a possible prior knowledge tool that you have the possible choices. And here, this is the corresponding table, table 6.5. And actually, you can try to check the range, and so that you can have the minima and maxima. And for these, actually, valid for both, for continuous or discrete distributions. And actually, you can have a mean and median, and this is a way to have a mean and median. And if you have this, why we want to use this one? Measure central tendency. And actually measure central tendency. In fact, even you have the central tendency. It says mean, median or mean. Actually, not true. So actually use this one. Perhaps this is the mean. And maybe some other point to serve as the median. Okay, so you can use how close to determine symmetry or not. That says if it is symmetry, and then we should have the really close mean and median. And that's why you can have the variance, and so that measure the variability. All right, and CV. Lattice ratio, CV for continuous, lattice ratio for discrete variable. All right, and if we have these, what is the purpose? Same as the variance. And in fact, you can have skewness. Skewness use the third central moment. And over standard deviation. Okay. Even if we want to have the measurement using actually the statistic, using the estimate, how to do this one. Maybe somewhat different, but at least we consider some specific, maybe some specific viewpoint to have some more accurate results. So that's why we have some actually some changes on the sample size. Okay, so about this, actually you can try to use some of the formula to make sure why we have these. Okay, at least the definition follow these, but for some statistic, you can alter the way to have the skewness. If you have a skewness, it is a direct way to have the measure for the symmetry. And this one actually different from how close about the median and mean and median. Okay, so you have the table. You can pass on the table to have some possible suggestion. All right, so that is a possible table based on statistics. So some of the given prior knowledge perhaps allow you to have the initial choice. However, in the following, we want to use the technique formally to check which one you need to select. First of all, you can use histogram. Histogram means if you have the possible data, you try to plot density function. All right, and if you can plot the density function, and then you can try to compare the shape. And next one about statistics, you can use a so-called quantile summary. And the so-called quantile summary serves as a tool to check symmetry or skew right or skew left. And actually, you can have the box plot. Later, you can understand what is a box plot. And the same box plot apply the information symmetry or not. Okay, so data check these. For continuous data set, and we want to have the plot. And the plot, actually, you need to have the number of intervals. And pass on the number of intervals to have the plot. If we want to select the number of interval, one rule of thumb, actually it is called the Sturgis. Sturgis rule, you can use the sample size, taking logarithm with the base of 2. And use the formula, you can have the number of interval determined by the rule of thumb. Actually, it is called Sturgis rule. You can use this way. All right, so you can have the plot. Actually, you can have the result for discrete one. And also you can have some specific checking for single mode or multimodal data. All right, because sometimes we don't have the multimodal. So that's why here we want to remind you of some specific selection. For example, here, multimodal data or not. And about that, we will have the details. We just let you know. You can have some possible choice for example, for the intervals. Actually, you can have the quantile summaries. Okay, about quantile, what that means, we want to know this one. Definition of quantiles. All right, so if we have a Q, okay, and Q, it is the probability. So if we have a half, this quantile, it is called the mean. If we have a quarter or 3/4, and this is called, the two are called the quartiles. You have octiles, or you have the extremes. Well, if we have the quantile, actually a quantile follow the definition here. All right. If you have the quantile, and then you can apply these to check symmetry or not. If you have all of these data almost the same, so you have the symmetry one. However, if you have the trend here, and it says skew right, and or otherwise median greater than average of quartile and greater than octile, and then you have skew left. All right. So skew right means positive skewness. So you can calculate skewness for sure. And you have a negative skewness. And so that you still can use skewness directly to have the checking symmetry or not. And of course, later we can that you have all the details. So here I just let you know, possibly you can pass on this information. Actually, you can have the box plot for the quantiles. And the same later we can check it. For example, here. Okay, so mean. Look at this. You can, oh, sorry, it is a mean. It is a median, sorry. Median. Okay, and the others quartiles, octiles, and extreme. Extremes. So you can pass on these, but you can have a box using the quartiles. And as for the others, actually you have a pair. For example, octiles and extremes. Only the median, you have a single point. Look at this, you have a median here. Median seems to be lower than the average of octile. So if you have this, what it means? This one. So this one, it is the skew right. Skew right, something like this. So the shape like this, it is called skew right. And actually you have the positive skewness. And likewise, you may have the other type of skewness, and so that you have the other box plot. Okay, so later we will have all detail to apply the previous discussion, and so that we can check the plot. Okay, so up to now, is it okay? Any question? If no question, later we can check it, but let us take a break for 5 minutes. So 5 minutes later, we can restart. Okay, so take a rest.